I hope you all did well on the quiz. I'm sure you did. So all of the gas laws we've gone over so far, Dalton's, Boyle's, Charles, Avogadro's combined, they're all about one gas and it changes. Pressure 1, volume 1, N1, T1, and that gas changes. Gets a new pressure or a new volume, whatever. Today we're going to go over the ideal gas law. And so you want to open up your notes packet to the ideal gas law. The ideal gas law is when you have a gas and it is not changing, but instead, if I know I have oxygen at a certain pressure and certain temperature, I can figure out what volume it has. And so before we get into the ideal gas law, the equations, and how to do the math really fast, I wanted to go back over, and you don't need to write this down because you've already written it down, the kinetic molecular theory. And so this is about ideal gases. The ideal gas law is about ideal gases. And so just going over these postulates. Ideal gases, the particles have no volume and they're very far apart from one another. So if I've got a container of a gas, whenever I'm thinking about, here's my little gas particles, they're far apart, and you can't find the volume of just one of these particles because they're always moving, they're moving randomly, and they're moving in a straight line motion, but it's not possible to get the volume of just one particle. Instead, you have the volume of many particles of gases as one. And so we say the particles have no volume because it's not measurable. They're very far apart. You should know that about gases. They move in continuous straight line motion. They have elastic collisions, so that means when gas particles hit one another, they hit each other and they move on. They don't lose any energy when they collide with one another. So no energy is lost from collisions. And that is true in ideal gases. Ideal gases don't attract and they don't repel one another. There's no attraction, no repulsion between the particles. They move just with no relationship to one another. And their average kinetic energy is directly related to their temperature. So let's say you have a gas at 200 Kelvin and a gas at 400 Kelvin. Which one's going to have the greater kinetic energy? It'd be the 400 Kelvin one. And we should say average kinetic energy. And I hope you know by now that kinetic energy is the energy of motion. So that would mean the particles in a gas at 400 Kelvin, they're moving faster than a gas at 200 Kelvin. So lower temperatures, things move slower. That, just think back to solids, liquids, gases, should make sense. Solids like ice, solid particles move the slowest, and ice is at a much lower temperature than steam, gas, water. Okay, and so where the ideal gas law came from, because again, I said the ideal gas law is not, and you don't need to write this down, it's not about a gas changing. And so if I just look at one side of the combined gas law, this right here, and if you actually take the combined gas law and you solve for 1 mole of gas at STP, now I hope you remember STP, that is standard temperature and pressure. For any gas, it always equals this number. And so this is actually a constant that's used in the ideal gas law. And our formula for the ideal gas law comes from the combined gas law and the fact that these variables, when you divide them out, they always equal this number. And this is the formula for the ideal gas law. Pressure times volume equals N, which is moles. R is the ideal gas constant times T. And so this is our ideal gas law formula. And again, this is used when you have a gas and variables are not changing. Unlike the combined gas law where variables do change. Now, the ideal gas law, it is a constant, so that number is always the same. It is 0.0821, and the units for the ideal gas law constant are liters times ATM divided by moles times K. So with that being said, if these are my units for my constant, that means when I use the ideal gas law, my volume has to be in liters. Volume can't be in milliliters when you use this equation. Pressure, when I look at this, the unit for pressure with this constant is ATM. So pressure with the ideal gas law has to be in ATM. Can't be anything different. Moles, well, moles is moles, that doesn't change. And then temperature, as always, is in Kelvin. So you definitely want to, write this equation down. 2, write down your constant, 0.0821, and then make a note that pressure has to be in ATM and volume has to be in liters. And that is the ideal gas law. We're going to do a few problems with the ideal gas law and calculations. And you'll see as we list our variables how you'll be able to tell, okay, this is not a combined gas law problem. The first example, so 16 liters of carbon dioxide are at a temperature of 45 degrees Celsius and a pressure of 638 mmHg. Calculate the number of moles of gas present. So when I go to list my variables, my volume, and you could even write V1, it doesn't matter. 16 liters, my temperature, 45 degrees Celsius, my pressure, 638 mmHg, and I'm looking for moles, which is in. You would list all your variables, and hopefully you would notice that there's no V2, there's no T2, there's no P2, etc. And so you have to use the ideal gas law, which is pressure times volume equals moles times R times temperature. And then make a note. R is 0.0821, and then hopefully, I hope you remember, pressure has to be in ATM. It's in mmHg right now, so we need to convert that. The conversion from mmHg to ATM, 760 mmHg, 1 ATM, that is 0.839 ATM. Volume has to be in liters. Volume is in liters. I'm looking for moles. My R is a constant. It's that number always. And temperature has to be in Kelvin. It is in Celsius right now. Add 273. And that's 318 K. Now I've got all my variables. I'm looking for N. Plug into the equation. Okay. Pressure 0.839 times volume 16 equals N times R, which is the constant, that number, times T, which is 318. And then multiply things out. When I multiply this side, I get 13.424 equals N times 26.1078. I'm trying to solve for N, so I need to get N isolated because they're being multiplied. So you got to divide each side by this number. Cancels out. What you do to the left, you do to the right. And we have N equals 0.51 moles of gas. And oh, it's CO2. That is using the ideal gas law. we've got 2 more we're going to do together. These should go faster. So 76,000 milliliters of compressed oxygen, which is again O2. It's at a temperature of 57 Celsius. If there are 7.3 moles of oxygen, calculate the new pressure. Listing my variables, my volume, 76,000 milliliters, my temperature, 57 degrees Celsius, my moles, 7.3, and I'm looking for pressure. So I would list my variables. Notice there's no 2 of anything, no V2, no N2, etc. So this has to be the ideal gas law. PV equals nRT. I know R is a constant. It's always 0.0821. And then check your units. Pressure, well, I'm looking for pressure, but pressure is ATM. Volume is liters. Right now volume is in milliliters, so we need to change that. Divide it by 1,000 to make it into liters. And that is 76 liters. N is moles. Let's double check, was that moles? Yes, it was moles. R, my constant. T has to be in Kelvin. So add 273. 330 K. And then ready to plug into the equation. I don't know P. My V is 76 equals N. 7.3 times my R, 0.0821, times my T, 330. And solve for P. P times 76 equals 197.7789. Divide each side by 76, and pressure equals 2.6. And remember, because it's the ideal gas law, the pressure unit is ATM. Easy enough. Hope so. And one more really fast. Now, this one is a little different because I'm saying the pressure inside a balloon is filled with 168 grams of nitrogen. There are 95 kPa, it's my pressure. And the temperature is 15 Celsius. Calculate the volume, so I'm looking for volume. I would look at this, PTV, it's an ideal gas law because there's no 2. Now, I know R, 0.0821, PV, N. N, you have to remember, is moles. I did not give us moles, I gave us grams. Now you can go from moles to grams and you'll be expected to do this, so don't act like that's a surprise. And so we're going to take our grams and change it to moles so that we can get our N, and then you can plug into this equation. Now, this is nitrogen. I hope you remember nitrogen is N2. Our diatomic elements, HOF, BRINCL. Nitrogen's one of them, so it's N2. And to change that, I'm just going to do that work down here. 168 grams of N2 times, I'm going to have the molar mass of N2 down here, 1 mole. Go to your periodic table. Nitrogen is 14.007. There are 2 of them, so the molar mass of N2 is 28.014. And so this is most definitely over 1 mole of gas. This is 5.997 moles of gas. You don't have to necessarily write that many sig figs, but whatever. You can leave it off there or make it 6.00. It won't change the answer, final answer, that much. And then now, pressure is not an ATM. Convert that. 101.3, 1 ATM. That's 0.937 ATM. Temperature is not in Kelvin. Add 273 to make it Kelvin. That's 288. and then you can plug into your equation. PV equals nRT. Pressure 0.937 times my volume, I don't know, that's what I'm looking for, times N, 5.997, R, our constant, temperature, 288. Ran out of room. And solve from there. Today should be these ideal gas law problems should be relatively easy. You just need to be careful whenever you are reading a word problem and making sure N is moles, not grams. If I give you grams, you have to change it to moles. So pay close attention to that. But these problems should be easy. Tomorrow we're going to do and there's our final answer. We're going to do the ideal gas law with stoichiometry. I was not kidding when I said stoichiometry also will never go away. And tomorrow will be the hard problems of the unit. So finish these, make sure you are good with just the normal ideal gas law problems before we jump into tomorrow, which is definitely a lot more tricky than this is. And so your normal ideal gas law problems are page, can't see that, 12 through 14 of your packet. And good luck.